So the world of serial is kind of an older world per se. This used to be how most of the world had things actually connected together back. The Ethernet, I'd say, is kind of the go-to standard nowadays. However, that's also, I'm going to call it, a little slightly higher level communication than serial. Serial, most things have a serial port on. You might not have access to it, but that serial port probably does exist. Things like barcode scanners, like you'd see at a food store, that is a good chance that is a serial connection from that barcode scanner to the actual computer doing the processing. It could also be USB now, but it also could be a USB plug, but it's actually a USB serial chip going on inside the little device. So it's still just a little serial connection right there. Up on the screen right now, I've got some, what are the kind of the standard serial connections. Most standard one is going to be this one at the top right here. This is a DB9 connector. Right? If you would turn this picture onto its side, it would kind of look, the middle shell look like a little bit of a D, and then there's 9 pins in it. Okay? So that's, I think, where the whole DB9 connector. But that is, as I said, probably the most standard serial connector that you're going to see. One at the bottom, that is, I think it's a DB25, if I remember correctly. It's out there, not quite as common. So, now, some vocab that you may hear. We have DCE, and that is your data circuit terminating equipment. That's your, this is the modem or generally a line adapter. So it has to transmit the clock signal which controls the data. We're going to come back to some of these too. We have the DTE. This is generally the terminal or the computer itself. And then we have RS, which is the recommended standard. And I've already hit up the DB9 and DB25. Now, when it comes to the world of digital communications, there's basically, we've got two worlds here, right? We've got the analog world and the digital world. So we're all in the analog world. Everything can vary. You push lightly against something, you push hard against something. You basically have infinite number of levels of pressure between that you can press. So we have very analog control. Anytime you get a computer into that system somewhere, you are now entering the world of digital, whether you like it or not. And you could be going analog to digital back to analog. Like that is something that is completely possible. You could say an analog temperature sensor reading, or an analog value reading how much water is flowing through a pipe, which then controls the analog pump that's making it spin faster or slower, push more or less water. So, analog sensor to a computer that makes the decision, then tells the analog pump what to do. So we could do analog, digital, analog. You could stay completely analog if you're going to go kind of old school. There are a lot of things out there that's all purely analog. But for the most part, digital has become the king. It allows a lot of flexibility. That is the whole reason I like it. But we have, how do we represent things in the digital world? Well, analog is continuously variable. So we can go from 0 to 255 or 1024 or larger, depending on how big your system is and how you have things configured. In the digital world, we have zeros and ones. That's all we got. All right, so we then have to start coming up with a way to deal with all of those zeros and ones. So how do we take zeros and ones and make them meaningful to us? Okay. So a single 0 or 1, that one little space. This. That can be a 0 or 1. That is a single bit. All right. Any 0 or 1 is a straight line. That is a bit. All right. So 0 or 1, you may hear it called high or low. You also may hear it called true or false. And probably realize there's a whole bunch of different ways that you can qualify this as, which is also kind of a pain of the way the world works. Now, once we take that 0 and 1, that one little spot, and we make it a whole bunch of spots, specifically 8 holes, so 2, 3, 5, 6, 7, 8, we now have what's called a byte. B-Y-T-E. Right? So we have a bit, which is one spot, and then we have a byte, which is 8 spots. Now, anyone know how many different combinations one byte has? One bit has how many? It can be a 0 or a 1. So there are 2, right? Yep. So one spot has two different combinations, a 0 or a 1. All right. So if I have two spots, how many? This could be a 0 or 1. That could be a 0 or 1. Who said it? 4. All right. I have three spots. Nope. We're gonna go longhand here. So 1, 2, 3, 4, 5, 6, 7, 8 different combinations. All right. And the simple way to figure this out is it's 2 to the number of spaces you have. All right. So if you have one space, 2 to the 1 is 1. We have two spaces, 2 to the 2, 4. Three spaces, 2 to the 3. That's 2 times 2 times 2. That gets us 8. Right? So if I have 8 spaces, that'd be 2 to the 8th power. You want to know off the top of your head? Oh, no, anyway, 256. There are 256 different combinations of zeros and ones. Notice I'm not writing those all out because that would just be ridiculous. But yeah, 256 different combinations. Another way to look at this is the ones column. So the first column is 1. And this would be 2, 4, 8. Doubles every time. I don't think I'm getting ahead of myself. But anyway, if there's a 1 there, you multiply 1 by that, and then you would add all these up. So if I put a 1, 0, 1, 0, I do 4 times 1 is 1. 4, 1 times 1 is 1. That would be number 5. So binary, which is what we have here, fits zeros and ones to decimal. Actually, pretty easy in the long run. So the opposite way, a little bit more complicated. But overall, this way isn't too bad. Now, the one thing here is prefixes. If I say kilo, what does that mean? You have a kilobyte of memory here. What does kilo stand for? Anyone know? What? Yeah, it's a prefix, so it's a multiplier. All right, so standard prefixes. You have kilo, mega, giga, peta, tera, usually it's tera, peta, but you also have milli, micro, nano, pico, those types of things. So if you go back to your wonderful world of math or science or whatever class it was, if you had the number 1,400,000, 1,400,000, yeah, you could write that out every time, and I'm going to call that I'm going to call that volts. Not you have 1,000,000 volts. We got some pretty crazy things going on. But anyway, you could have 1,000,000 volts, 1.1, yeah. But we could also write that as 1,400 kilovolts or 1.4 megavolts. 1.4 megavolts is a lot easier to write out than 1,400,000 volts. So prefixes allow us to basically, I'm not going to call it ignore the data to the right of the decimal place, but it kind of simplifies our life, makes it a little bit quicker when we're trying to write things out. So you will have in the world of computers, you all probably heard of kilobytes and megabytes and gigabytes, right? Well, your hard drive or your RAM, that's how we measure the size of those things. Because writing out, when you have 1 terabyte, so mega, right? Kilo is 10 to the 3rd. Mega is 10 to the 6th. Giga is 10 to the 9th. Tera is 10 to the 12th. All right. So if you said, oh yeah, I've got a 4 terabyte hard drive in my computer, which some of you guys might have a 1 terabyte hard drive, depending on how fancy your computers are. That'd be 1 followed by 12 zeros. You want to write that out every time that you had to tell someone how big your hard drive space was? I definitely do not. So now, the reason I'm going through all these prefixes is, we normally think about kilo as 1,000. 1,000 flat. We're done. All right. However, it's not that black and white in the world of computers. Reason B is trying to stay over here by the computers. That's why I'm working all this stuff reason B. So 2 to the 8, that is 256. 2 to the 9 would be 512, and then 2 to the 10 would be 1,024. So, if I wanted to say I've got 1 kilobyte of memory, all right, that's 1,000 bytes. Well, we just want to ignore those 24 bits. Not bytes, sorry, bits. Go back to the world of bits here. We want to ignore those 24 bits. That's like throwing them out the window. So in the world of computers, the prefixes are always 1,024. So you just have to be kind of careful about that one. That also, I believe, is the reason why if you look at like a hard drive, it's like, yeah, you got a 4 terabyte hard drive. But if you actually look at it, it's not truly 4 terabytes. It's like 3,000, 3.9 terabytes or something like that because of all that other big things. So just something to be aware of. You also do need to be aware of bits versus bytes. And I'm saying terabyte hard drive. I think it's terabyte or spelled terabit. Say byte. I'd have to look that one up. But anyway, bit versus byte, you have to be very careful about that. And you know who's great at not using bytes or bits? Your internet service provider. All right. This bothers the living daylights out. Most computers are working in the world of bytes. Right? 1 bit, 1 little 0 or 1. That's not a lot of information. You get the bytes, you at least start having a little bit of something. But your ISP is like, yeah, you have a 50 megabit download speed. And then you're downloading a file at home, and you're like, why am I only getting 6 megabytes per second download? Like, I'm supposed to have a 50 megabit connection, right? Well, bytes versus bits. 6 times 8 is 48. That's pretty close to that advertised 50 that you're supposedly getting. So you need to be kind of, not careful, but just be aware of when someone's advertising like transfer speed and things like that. Is it a byte, which is a capital B, or is it a bit, which is a lowercase b? That is the whole difference when we're writing them out. So just like to point that one out for all you guys. Anyway, here I have what's called the ASCII table, the ASCII table. All right, and this is where we actually start being able to deal with the whole world of bits and bytes and things like that, and actually storing data in this. Just like we all speak the English language, your computer speaks the ASCII language. All right? So if you were to write out 7 numbers in a row, one of those, it would correspond to a specific letter. We have this table that said, hey, I need to transmit this data over a serial connection from computer A to computer B, and I'm going to send it 1001110. That to the receiving computer, that's going to go, oh, okay, that specific pattern of code means 0. So I now know that I should display a 0 on the screen or a Word document or whatever the case is. If you did 1000001, that would be the letter A, and that would be more specifically a capital letter A. All right. So up on the screen right now, I have the 7-bit. Some of the stuff from the 7-bit code, which only has 128 different combinations. This contains both capital letters, lowercase letters, numbers, and symbols. All right. So as a quick little lab activity, give you guys a minute. At the bottom of the screen, I have 1001001, 1001110, blah 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 blah. Go ahead and decode that using the table. So stand for a while. So shouldn't be that much to do, so let's just go sign. Yeah. That's not very good. I don't know all this very much. Let me tell you, kind of we've been students in my classes and watching myself speak, freaking hilarious. Having someone sign what the hell you said. think I know what this says, if I remember correctly. Should really put it in my notes. Yeah, okay. Took this from another class, so it might be a little, not making yeah. But it will. All right. That's the first letter. What? I is the first letter. Second letter. N. Third letter. T. INT. All right. This I think I pulled my nails class, but I don't take the class on it. That doesn't really well. So need to do that one. But anyway, so that's just a small portion of it. You also have the large portion. There we go. All right, so this is all 127 different bits. So you can see we've got, starting with the second column, all of your kind of standard characters, letters, symbols, those types of things. Before that, we've got some other kind of crazy things going on. So like a 000, or 0 is null, start of heading, start of text, end of text. Got a whole bunch of other crazy things going on there for control purposes. And carriage return, that one's actually kind of important. Enter. What's the other one? New line. Yeah, so LF and carriage return. Those do not quite mean the same thing. That drives me absolutely. You guys ever have to start dealing with like serial? I'm gonna hit enter, and it doesn't send the actual enter command, but I want to send it enter. But you have to tell either a new line or carriage return or those two things. And depending on what the hardware you're talking to, that's going to matter whether you send new line or carriage return. So it starts to get really kind of annoying at that point when you are dealing with this type of thing. So just something to be aware of. This is kind of interesting to me, maybe not to you guys. We have the decimal, so the number equivalent. You have the hexadecimal number equivalent. Then you have the octal number equivalent. And then we have the actual character that we're sending. So it's just, to me, that's kind of interesting. And then over here, we actually even had whole HTML thing into it, which is, man, there's so many different ways to send the letter B over something. So, if you want to expand this past 127, so we go back to the whole world of 8, here we start adding more symbols and things. So 127 is really probably what you need for most communication, but sometimes you might want to use some of these fancy symbols for whatever purpose, umlauts and things like that. So. All right, we got some. I think I got a clock in here. And 40. All right. So when it comes to electrical signals, we've got two different things. We've got this serial, RS232. But really, no matter what it is, I guess this is starting to get the real world. So far, we haven't really been specific to serial or kind of talking about communication. Now we're going to start actually getting into it. So, you have only a serial communication. There's mainly the standard called RS232. There's some slight variations on this, which makes it really freaking annoying. Can't you just get one standard and be done with it? Make that work for everything? And the answer is no. And to be fair, there are actually good reasons. We'll come back to it. But anyway, so a transmitter, if it's going to send out a logic 1 on the RS232 network, it will send out a voltage signal between -5 and -25 volts. Okay? Negative for a positive for a 1. I hate anything that's inverted. like wire size, measured in gauge. The larger the wire, the smaller the number. How do we have to go backwards? It just doesn't make sense. But anyway, we have inverted logic here. So if you're going to send a logic level 1, it's -5 to 25 volts. If we're going to send a logic 0, it's 5 to 25 volts. You will also notice that there is that undefined logic level, that -5 to 5 volts. So just kind of something that you do need to be aware of. Now, however, on the receiving side, this is the part that I find interesting. Notice the receive logic level 1 is not 5 volts, -5 volts, it's -3 volts. You'd be like, you're sending me -5, why do I accept now the negative? No? Actually, signals. As we send big power over electrical wire, we lose energy. That wire has resistance. And if we go to Ohm's law, which I don't know if you guys know, but Ohm's law says voltage equals current times resistance. Voltage is the electrical push, that's how hard we're pushing the electric signals down the wire. Current is how much energy we're actually using. Overall, it's the flow. How much aside, if we go back to the world of water hose, voltage would be the pressure, how far that stream of water is going to shoot. Flow would be how many gallons per hour coming out. That'd be your current. But anyway, you can figure out how much power loss we have, because you can say, well, 1,000 feet of this cable has 2 ohms of resistance loss, and if we're going to be running at 5 volts, we can figure out how much current we're going to be using. How much current, we can figure out what our voltage loss is. So because of that, we don't want to say, I can transmit 5 -5 volts, and you have to be able to receive it. You want to be able to have that slight voltage drop there, so that like, as long as you're sending me a good signal, I am still accepting it and saying, okay, that's high enough, I'm still good. This is also why that voltage is important, why we have that range from -5 to -25 volts. The higher the voltage, the longer distance we can go. And without losing that signal. So that's why that high voltage is extremely important. So, yeah, so that's why we have those slightly different voltage levels there for receiving and transmitting. We still do have that undefined voltage range on the receive side, which is -3 to +3. So really, you've got 3 states, right? You've got the logic 1, the logic 0, and it's like undefined ratio. The other thing that is really interesting to me, let me actually just draw this one on the screen. You're sending these signals and they look like this. All right. However, imagine those lines are being like perfectly vertical, because I can't draw that accurately with a mouse. However, what they truly are is something more like this. There's more of a slant happening. It's not this perfect vertical transition. Now, it's not going to be as bad as my drawing, as crazy, as slow. I don't have a time frame on this. This isn't like, over 1 second we're going to have this drop here. No, it's going to be like a millisecond or whatever. But there is still going to be a plummet there, right? So it is important to just kind of recognize that. So it actually is going from like this one state to an undefined to the other state whenever we transition. It's always going through that. It's not just like instantaneous. We flip-flop it. It's kind of like a light switch in your house. If any of you guys have 3-way light switches, you can like put the one in the middle. I don't want to do Jack Sibley. I remember doing that to my brothers when I was a kid. Let me put the light switch in the middle so they can't turn the light on and I have to walk down the hallway. I don't know how I was thinking like that, but I just very vividly remember that one. But yeah, so we do have that what are we calling it? Undefined. So, yeah, the last one I have on there is TTL. All right, TTL stands for transistor logic. What the hell is transistor logic? Anyone have an idea? Okay. Not really probably surprised, but that's fine. Yeah, so when we're communicating over long distances, a few hundred feet or maybe even more, I don't know what the range off the top of my head for Cyril is. I think I might have that later slide. But we're cruising at long distances. We need to have high voltages so we can have power. However, computer processors, anyone know what voltage those things run at? Your standard CPU is like 1.2 volts or something like that. The voltages there are extremely low. One of the reasons I like these lower voltages is when they have transition, there's a much smaller distance to transition from 1 to a 0. It means they can do it quicker. Right? If you need to transition from a 1 to a 0 and you're on the top of the building at the bottom, right? Every time you want to send a 1, sending coded messages to somebody, you're like, hold on, I have to run up to the roof. Imagine how long it's going to take you. Or if you're like, I have to go to the top of the car, it's like a half a second or 2-3 seconds to do that, where it might take you 30 seconds to get to the car. So the lower you can get those voltages, the quicker you can transition from one to the next. Right? But anyway, transistor level is instead of negative 25 to 25 volts, we are 0 to 5 volts. That's our distance. So instead of having such high voltages and big distances transit, we only have these little voltages. And the reason for that is what computers actually deal with. They're normally smaller voltages. That a lot of, especially older microcontrollers or Arduinos, for those who have heard of those, the older ones are 5 volts. If you're starting to get to the new world of microcontrollers, like ESPs, those are only 3 volt devices. So when you're trying to do a serial communication with it, it's only a 3 volt signal, not a 5 volt signal. And so if you're trying to do something right from your CPU to CPU, like on board, it's only like 1.2 volts. So our voltages kind of keep coming down over time. Originally, I was really annoyed by the whole different voltage thing, but I just something you got to deal with. So overall with TTL, since we don't have that negative, we have a 0 representing, I believe, a 0, and a 5 representing a 1. All right, and these again are not really meant to go long distances. Not big, be like 4 or 5 feet type of thing. Cable on the computer going to the device. That's so that barcode scanner might be TTL based, or it could be a traditional RS232. Just something that you kind of got to keep in the back pocket. Now, can you use a TTL device with an RS232 device directly? A TTL device is sending out 0 to 5 volt signals. My RS232 is expecting negative 25 volts. Can I use those natively together? Yeah, right? Because the one never goes below 0. So we have to have some sort of adapter in there, or line driver, as my notes call it. But there is ways to do it. It's a matter of being able to say, oh, that's a 0. I should send a negative 5 volts out. Oh, that's a 5. I should send positive 5 volts out. So we do have those possibilities there. All right, so electrical connections. When it comes to RS232 or serial, we've got a lot of options. And I mean, the DB9 port there, we have all the different options up there. There's the DB25, in theory is up to 25 of them, but we're not quite there. But anyway, let's go back for a second. So we do have data lines, all right? So those are going to be your transmit data and your receive data. Those are pretty much, I think, pretty spelled out for you. Pretty nice. That's nice. You do then have control lines. And the control lines, this is, as far as I'm concerned, when things start being a bit more. Oftentimes, if you guys get into the world of TTL serial, all you do is ground, transmit, receive. 3 wires, you're done. So all you need to know is there's data coming in, and I need to be able to send data out, and I need that ground, that 0 ground rail, whatever you want to call it, to have a complete loop. As long as I got those 3 lines, I can talk to other devices. On the world of serial, it's not quite that simple for RS232. So control lines are used for interactive device control, which is commonly as hardware handshaking. And this regulates the way that data flows across interface. So instead of, normally you guys have something to say, you might raise your hand or whatever, and I'll say, yes, go ahead. And you'll say what your piece, and then we'll move on. That's the same idea going on here with the serial control lines. They're allowing the devices to talk, saying, hey, I have something to say. And go, all right, go ahead and send it. I'm ready to listen. Instead of always having to be ready to listen. Our 4 most common used control lines are RTS, which is the request to send. So device A would say, hey, I have something I want to tell you, and it would bring that line by. And then the other device would say, CTS would go, clear to send, go ahead and tell me it. And then we also have data set ready, or this is either DSR or DCE, depending on which protocol you're following. And then you also have DTR, which is your data terminal ready, or DTE. So again, two different options there, which drives me freaking batty. We also then will have timing lines. All right, timing lines are when should I be sending information or expecting to receive it. And there are two different ways that we can do this. We can do it synchronous or asynchronous. So synchronous being, I'm going to send a pulse out. So I'm going to consistently send high, low, high, low, high, low type of thing going on here. So I'm going to just do something like this. And this is just, these are all supposed to be perfectly spaced, so ignore my high quality drawing. All right, and then, so this would be your timing. And then your actual data line would be down here, and it's sending whatever the heck it feels like. All right, but by having both of those, the receiver knows, here's a piece of information, there's a piece of information, there's a piece of information, there's a piece, there's a piece, there's a piece, there's a piece, there's, it knows when it should be saying, all right, what's the controls, what's the signal right now, high or low, and it's able to then determine. All right, so that'd be a synchronous base. So you have a data signal being sent, and it's saying, okay, I'm reading at this. You can also do asynchronous, which I think we'll come back to in a minute. Going back here for a second. Hardware handshaking. This is the cause of most interfacing problems. Relying on that, and it's because I do it slightly you and all this game. There's not a perfect standard set. Most of the time when I've dealt with equipment, I've not done synchronous, I've not dealt with handshaking, it's all TTL based, it's just, are you, sending data or not data? It's simple, 3 wires and I'm done, so I haven't really had this big of a problem, which is nice. Some manufacturers omit the control lines from the RS232 equipment or assign unusual applications to them. So again, lack of consistency. All right, so let's go ahead and look at these connections again. So here you can see our DTE and to our DCE. So we have our computer to our modem or whatever device it is that's sending out that information or receiving that information. And you can kind of see how things actually are lining up here. So you've got your carrier detector, your CD connected together. In this case, our received data connects to our received data. And I will say, that one to me is actually a little backwards. Especially sometimes when you're reading this stuff, you're like, I have 2 microcontrollers, I want to make talk to each other. You take the transmit of one to the receive of the other one to the transmit of the other. So you're actually crossing those lines. All right? Which, when you think about it, if I'm transmitting information, I don't want to talk to your mouth, I want to talk to your ears. All right? So I talk to your ears, you talk to my ears, we're all hunky-dory. All right. Where if I'm talking to your mouth, obviously you can't take that information in very well. So kind of important to cross those lines. So it's really one of those things you have to be careful about when you're setting stuff up, especially if you're like manually making connectors or something like that. Just be aware of, did I cross something? Did I not cross something? But anyway, then you can see our DTR, and again, these are all like just straight throughs. But it tells you which one's sending information in which direction. So speed versus transmission length. All right, baud. Anyone know what a baud rate is? Love to hate it. Or learn to hate it. The baud rate is how fast we are sending. So you have an old, you're setting up a barcode scanner on assembly line so you can make sure whatever product is whatever product. That barcode scanner died one day. He went, all right, let me go to the stock room, grab the new one, plug it in, we'll be fine. And then you're like, this damn thing ain't working right. Well, one of the things that you might have to set is the baud rate. How fast am I talking to you? All right, so this goes back to the world of being asynchronous. Me a little backwards. Overall means that I am not sending a control timing signal. I've told you I'm going to communicate with you at this rate. I also like them about the language, right? I tell you, I'm going to talk to you in English. You're like, okay, cool. And then if I start speaking French, you're like, what the hell? I thought we were talking English here. But if we're not talking at the same rate, you're not receiving information as quick as you were expecting. Right? So that rate becomes really important. So the baud rate is how fast we are sending information. This is normally given in bits per second. Notice we said bits and not bytes. All right. Yeah. Anyway, so up on the screen, I have some different baud rates for distance. So if you notice, the higher our baud rate goes, the lower our cable. Right? Anyone have a really quick, rough how to transmit convert from meters to feet? Roughly multiplied by. That's like your stupid simple answer. Right? A meter is roughly a yard, right? And a yard is 3 feet. But you can just kind of, when you go from meters to meters, you just basically just 3 multiplied by 3. These are meters. Put that 2,400 feet. Right? How many feet are in hollow? 5,000 feet. It doesn't really matter. That's what happens with the that we can communicate with a serial communication. And already 100%. Right? So this goes back to the whole why do we have baud rate affected our cable length affecting our baud rate? And that goes back to the whole transition. Why can we not have this exchange from a high voltage to a low voltage or negative voltage? Say that again. Why can we not have that instantaneous, positive 5 volts to negative 5 volts? Okay, I mean, it's not just traveling down the wire. And my microcontroller can be pretty darn instantaneous about this. Right? The problem really becomes with the length of the wire. When you put two things right next to each other with electricity in them, anyone know what that's called, basically? Normally it's a little can circular device, 2 leads coming out on a circuit board. Is it? Close. Right idea, wrong component. Stores energy slightly. Capacitors. All right. When you take two metallic devices, put them close, not touching, that'd be dead short. You basically are creating a small capacitor. So the longer your wire, with these two wires being right next to each other, because there's 2 of those in that cable, the bigger that capacitor becomes. And capacitors store energy. So if at one moment I'm telling you, hey, here's 25 volts, and the next moment I'm telling you, here's negative 25 volts, it's like, hold on, I got to drain my voltage down, right? Like, let me dump the pitcher out. Kind of think about that. The longer the wire is, the smaller the hole that you're dumping that water in. All right? So it takes time to uncharge and recharge that capacitor in another direction. That's why the length of the wire matters. By keeping the wire shorter, we have a smaller capacitance there, which means we can transition. All right, and because of that transition period and that capacitance getting longer with the longer the wires, we can't take a reading as often, because if we would take a reading right here, it'd be in that gray zone. We'd going, what the hell does that mean? So we'd have scrambled data is what it comes down to. So length is really important here when it comes to your baud rate. This table right here is based on field tests. So this isn't like a theoretical, math. According to the math, we can do this. Now this is we've actually tried this, and in the test environment that this was done, these were the baud rates that. Okay. Now the other nice-ish thing here, I'd say 9600. That is probably your most standard baud rate right there. That is the one that you will probably see the most often. All right, that's kind of like the default go-to. I don't know why. I don't know if that's it's 70 meters, like 200 feet. I don't know if that's just a good, average foot number that most people are going to be running cable less than, so we can, use this in a very wide range of applications. I don't know why, but that's the one that I always see. Is the default go-to is 9600 bits. Yeah. So other common ones that I've seen, probably the next most common one is this one. But I think I normally actually see it with a 2 here, 1150-200. All right. Now the other thing I will say is, while these are common baud rates, you don't have to be angry. You feel like I need every ounce of speed I can get out of this cable. But I'm at 600 feet or 600 meters. Like, well, according to that, I would have to use 600 baud rate. Like, can I bump that up a little bit? And as long as both devices support like a specialized baud rate, there's nothing saying that you couldn't try bumping that up until you start saying RS. And then backing that off a little bit. But you could do that. Okay, as long as both devices understand how fast you're communicating, perfect. So going back to my barcode scanner, saying, oh, you plug this barcode scanner, it's not, you're getting scrambled data. Probably have the wrong baud rate or other settings set. I actually find it really interesting. Barcode scanners to change the settings, they're like, there's no screen on them, right? You can't just click some buttons. They scan barcodes. They have in the manual, there's a few pages of barcode. You're like, oh, you want this baud rate? Scan this barcode. The barcode scanner reads that and goes, oh wait, I should be changing to this. It actually knows those specific barcodes, which I just find really interesting. Oh, okay. I was going to bring this up. We'll come back to the sequence of steps in a minute. All right. Null modems. These are basically the whole point of a null modem, as you can see here, our RX and our TX data. Those get flip-flopped, so those are important. They got some other stuff getting flip-flopped, our RTS and our CTS. But notice our CD gets pulled down to our DSR and things like that. But the whole point here is basically it's to trick each other. So when handshaking doesn't work, you can try putting a null modem between them, and hopefully that will trick both devices, saying, yeah, the handshaking is working just fine. Not working right now, but maybe this will fix it. So that's basically the whole point of a null modem. And this could be for the same gender or for different handshaking requirements. So, and traditionally they cause more problems than they actually solve. So not really the best idea of using null modems if you can avoid it. All right. We've already talked about some of the stuff. So serial communication, single bit of data being transmitted at a time. So a 0 or 1, just 0, 1, 0, 1, just pulsing that stuff out. As we already talked about, synchronous, we have clock line required, so that constant 1, 1, 1, 1, just sending a little pulse saying, this is the data, check it, check it, check it, check it. And then you have that asynchronous, which I said has no external clocks required. And that's going to be the one that's more common, is the asynchronous. Whether that be good or bad, that's up to you. So with the synchronous, it might hear it called spot. You might hear a protocol spotting, serial protocol interface, or integrated, interconnected. I2C, something along those lines. I think we're going to come back and talk about this another day. So those are those two. And then when it comes to asynchronous rules, when you don't know, but when we don't have that problem, how we're transmitting data, we have to set up something. I have to tell you some information so you know what to expect. So here we have data bits. So the section right here in the middle. This is the fun part. 5 to 9. You can have 5 bits or 9 bits, or anything in between those of information. Yeah. 8 is somewhat the standard. We like talking about bytes. I like being able to say, here's a byte of information for you. I'm going to send a whole byte of information. Now, as well, again, the most important part here is that both devices are configured the same way. If I say I'm going to send you 8 bytes and you think I'm only sending 6, everything becomes haywire. So having those devices set up the same way is the aspect. So we have our data bits. We also have synchronization bits. That's the start and the stop. So we have our start and our stop. Those are our synchronization. That's going to mark the beginning of the data and the end of the data. So the start takes the data line from a 1 to a 0. That's kind of like the, hey, start listening. And it's like, oh, crap, I got to listen. And then, then the data gets spit out. And the stop takes the data line and leaves it back at a 1. So it's going to take it to a 0 probably and then back up to a 1 or something. Those lines. Then we have parity. And this one is actually somewhat important. Anyone know what parity is? What? Rather unambitious. Right? So parity is all about the data I got, is it good? Did I have any problems? Is there any interference? Something happened to that data that I received. And then luckily, if you don't have parity enabled, you're kind of blindly accepting that what you got is what you were supposed to get, and everything's all hunky-dory. Now, that can become problematic. So this is a very simple form of error checking, parity. All right, and it only can detect odd number of errors. All right, I just got it. What the hell do you mean by odd number of errors? All right. So what we do with data, with parity, is we add up the value of all the data that we have. So if I have 5 bits of data, I have a 0, 1, 0, 1, 0. Here we go. I would have, if I add up those numbers, I'd have 2. I have 2 ones. All right. And what parity is, we have 2 versions of parity. This is also where it gets confusing. We have even parity and we have odd parity. All right. Even parity, once we're going to add 1 digit here. So parity adds a spot right here. And basically, the goal of parity of even parity is to make the value of the data plus the parity bit even. All right. So here I have 2 ones, so that's 2. Is 2 an even number? Yes. All right. So the parity bit would be a 0. All right. If my data was odd, I had 1, 1, 0, 1, 0, and I was still doing even parity, it would be a 1. So that way, when you add up all that information, that number is always going to be an even number. This is why I say we only can detect odd bits, odd errors. All right. So if only one thing gets flipped, and instead of getting 1, 1, 0, 1, 0, you get 1, 1, 1, 1, 0, with our even parity there, you would say, that's 5, I'm doing even parity, something's wrong. But if 2 things got flipped, it can't detect that because, well, one went from 0 to 1, one went from 1 to 0, and I still have even parity. So it can only detect odd. Even if you have odd parity set, it still only can detect odd numbers of errors. So up here I have even. So when we add them up, it always adds up to an even number. Odd would mean it's the exact opposite. It should be an odd number. You think they could just be like, even parity is the only thing that exists. I don't know why we have to have even parity, we have to have odd parity. Like, that just adds a level of complexity that is not necessary. But it exists. And on top of that, you can also have no parity. So you have even parity, odd parity, and no parity. So we're not actually error checking. We've already talked about baud rate. Yeah. So, biggest important thing here when it comes down to serial communication, in my opinion, is making sure everything is set up the same. Devices A settings are the same as devices B settings. As long as that's the case, you should have pretty small or non-existent errors in getting those devices to communicate. Mixed up baud rate is probably the one that's going to happen the most. You're going to plug a new device in, and it's supposed to be this baud rate, and it's not, or you had your old baud rate set high, you plugged in the baud rate, that you're like, oh, that's the default, 9600, perfect, plug it in, it did work. And when you do that, you get all sorts of weird data. One of these days, I will show you guys. So here is, if you're talking serial with somebody, 96.8N1 is a way to very easily tell someone what the configuration is. Right? So in this case, 9600 is our baud rate. 8 is the number of data bits. N is telling us we have no parity. And 1 is telling us we have 1 stop. So 9600 EN1. You may also hear 11,5000 6E2. No? So 11,500. No, sorry, 115,000 would be our baud rate. 6 would be our data bits. We'd have even parity, and we'd have 2 stop bits. So that little thing right there is just like the short, simple, sweet one. 9600 8N1 is kind of like if I had to guess, that is where I would start. That would be my first go-to for a baud rate. We'll talk about that next class. I got 2 things to cover for this one still. All right.